It looks like we have a couple people who have not joined before. Dan, you haven't been on one of these sessions. Would you like to introduce yourself here?
Hi, I'm Dan Connolly, software developer for a few decades, used to work on web standards and doing RChain stuff since last fall.
Cool, thanks. And then Tomislav? Ooh, I'm not hearing you right now. You might be muted or no mic connected.
Do you hear me now?
Yeah, I do.
Okay, great. I'm Tomislav from Croatia, and my background is in electronics, and I was working with electronics for about 10 years, and last 10 years I'm working mostly in .NET and web applications, and I'm following Greg and for about 2 years, and he joined Scenario, so yeah, I'm interested in learning PyCalculus and raw calculus. Yeah.
Awesome, great. Could I get people to mute your mics when you're not talking as well? That'd be great. And anyone else who hasn't been to one of these sessions that would like to introduce themselves? Dog, I don't know if have you been here before?
Oh, I've been in almost all the sessions except one. But yeah, I'm David, in case nobody noticed. Yeah, I'm in Germany. I'm part of the in Block Your team. So we and a lot of our people were there at the DEF CON in April in Denver. And that was our first deep dive into RChain and Rolang. And yeah, I'm following along the sessions with Jake to just get a much better understanding of PyCalculus, K-framework, and those things.
Okay, awesome, thanks. And I believe, Will, you were here last week, right? And Nikita as well. Did you introduce yourselves?
Yes.
Yeah, okay, great. Hey, yeah, good to see you.
Hello, I'm Will. I'm from China. And I have been here last week, so I'm coming here to speak too. Glad to see you guys.
All right, awesome. Yeah, good to see you.
Hey, Will, we are exchanging some emails, right? You are this Will?
Yes.
Okay, cool.
Great. Awesome. Good to see people connecting.
I think I met David also and Glenn in Boulder.
Ah, nice. Yeah. I was in Boulder as well, but I guess we didn't cross paths.
Yeah.
Cool. All right. Well, so I guess let's just start by asking if there's any questions about last week's session with Greg. From my perspective, there was pretty much two things that were introduced. And the one, which was sort of the biggest, was this sort of new type of COM rule, where we're stating that in row calculus, one of the things that's defined is we use structural equivalences of processes as name equivalents, and we use that to define how reduction can take place. Is if the input channel and the output channel are coded processes that are structurally equivalent, but there's no need for that to be the rule of interaction between those two names. So, Greg introduced another form saying that you could say that you have two channels where if they reduce when they're put in parallel to the ground process in 0 or some n number of steps, then that is when those two channels are in a channel and co-channel relationship and allowed to have a reduction across them. So yeah, what questions or comments do you have about that? And I guess I can also just say that the other thing that was sort of introduced quickly at the end was this notion of creating a context for processes, which is sort of like a way of and I had trouble understanding all of this, and I'm hoping that we go into it more next week. But I think it's a way of sort of wrapping up a process, accepting a process of a certain sort of kind, adding a whole bunch of computation to it, and so then we can take our COM rules and say that continuation or that context is what wraps up a process, allows us to do any sort of transformation we want to it before sort of substituting it in our COM rule, and that these things can be composable. But I don't really know where to find more information diving deeper into this. I don't know if anyone else found anything more about context. It looks like, actually it does look like in the PyCalculus paper, the tutorial, there's, it gets into context a little bit, and I think those are probably similar, but I haven't followed all the way up on that. So, but I think those are sort of the main two things that we talked about last week. And then in terms of continuing talking about exercises, you know, we could talk more about the K-framework stuff. I haven't done much work on K-framework in the last week, but if anyone has any questions once they've started exploring a little bit further, I'd be happy to go into that. And then there's also there's the implementation of the row calculus in sort of other programming languages. So I have a Scala implementation that I've done that maybe has a few quirks and isn't, yeah, but I'd be happy to go over this sort of line by line if we wanted, or answer any questions about it. And then we also have Greg's row camel implementation of the row calculus, which it looks like it's actually a type of the row calculus he's going to introduce to us later, which has the spatial considerations inside of it too, which I'm not totally sure what that means yet or what that does. But you know, I think the structure of this OCaml implementation might be interesting to look at. And then I know that Dan, you are also working on an implementation in Idris, so we could look at that as well. But I will stop there for now and let discussion decide where we're going from here.
I just want to find this paper here that you've got on the screen.
Yeah.
Oh, this paper that I have on the screen, this is the row calculus paper. Let me. I usually get to it by Googling row calculus, hitting the Wikipedia page article, scrolling down to the bottom, and getting to Greg's 2005 paper.
I would be very interested in discussing that COM annihilation. I did not get a clear grasp of that, but I found it really interesting. So
cool.
That would interest me.
Yeah, I also even struggled with the part on top of the bar in that COM annihilation rule. I wasn't even sure what the prerequisite was saying exactly.
Okay, great. Yeah. Let's go over that then. Yeah. So I guess, yeah. So does the framing make sense that we're setting out to define a COM rule or a reduction that doesn't necessarily depend on, so I guess we'll scroll up to the other one. So right here we have two channels that are in this relationship in that they're name equivalent. And that's what decides that we have a communication that can happen.
Two channels?
Yep. So as x0 and x1 are names, and they're name equivalent. Oh, and I guess channels can be used sort of interchangeably with names. I usually use the term, those are interchangeable terms. But we have these two names that are name equivalent, and that's what tells us that, you know, if we have an output and an input that are both listening on these same name equivalent names, I guess, yeah, I use channel, I guess, when I'm talking about like constructing a name, you know, so the name.
So when you say name equivalent, you mean you could alpha convert to exactly the same?
It might not only be alpha. It might also be any other of these
Structural congruence.
Yeah, any other sort of structural equivalence of the quote. So names are just quoted processes, right? So name equivalence, as it's laid out here, is structural equivalence on quoted processes, which then just goes to name equivalence again. So they're embedded within each other.
Right, that recursive relationship. Right.
But yeah, a name equivalence can be reduced to a structural equivalence, which can be reduced to a name equivalence. And at the bottom level, you have you have the structural equivalence of a process, because that's our bottom level entity in the row calculus. And then yeah.
Do you think it's possible to create a tiny example? Do you think, or is that too much?
Yeah, sure. Let's see.
I was just gonna.
Can you also relate this to this Scala implementation or your Scala implementation?
Yeah, that's a good idea. We can totally do that.
Yeah, we should be able to make a test case, right?
Right. So let's see. Let's see if we can just do this on the fly with this.
For me, it was difficult to understand what is the lift and drop in the context of what Greg's are explaining.
Lift and drop are input and output. It's kind of weird. No, wait, they're quoting, you know. Okay, never mind.
Yeah, well, lift is output and drop is unquote. But when a lift also can maybe kind of be seen as a quote a little bit, in that when it needs an input, its process gets quoted.
Okay.
So, Glenn, to cook up this example, if we're looking for two things that are name equivalent, can you think of two processes that are process equivalent?
Yeah.
Well, the canonical process, I think, of is just a send and a receive, like just a simple com rule. But
wait, those are equivalent? Those
no,
are
not equivalent. But you could take two of them, I guess, is what I was thinking. That. Yeah, I don't know. I don't have one in mind.
So,
I mean, I would guess the empty process, even if that works. I'm not sure.
Well, what's it equivalent to?
So we have the zero process, and then we can have.
Well, the process that sends on the empty. Two processes that send. Interesting. I don't know.
Well, you might want to go and look at the rules for structural equivalence then. But anyway.
Well, so if you have a process that's a par of a send and a receive, that's the com rule. If you have two of those, but the names are different.
But the com rule is not part of structural equivalence.
But two processes that are structurally equivalent.
Yeah, but that's what we're trying to cook up.
Exactly, that's what I'm saying. So if you have two processes, each of them are pars or parallels, right?
Okay.
And one side of the parallel is a send, and the other side of the parallel is a receive. Mm-hmm. Now, if you have two of those pars, and the structure is exactly the same, it's both a send and a receive, but the names are different. That would be structurally equivalent, but I don't know about name equivalence. I'm not. It would certainly be alpha equivalent as well.
So, Jake, I think I can see what you're about to do here, but can you show the rules for structural equivalence of processes?
definitely. All right, so here is part of structural equivalence, and this is the part that is not alpha equivalence, but alpha equivalence is included as well.
So the first one is that P par 0 is structurally equivalent to P, right, Glenn?
Yep.
And, you know, P par Q is structurally equivalent to Q par P.
Yeah, okay, so we could just take two pars and swap them back
Right, bingo.
left and right.
Mm-hmm.
Yeah, you can either use the first rule or the second rule, either way. Okay, so now, Jake, go back to what you were doing.
Right.
I'm curious about the example Glenn was describing, because my intuition was also that those were structurally equivalent. Is that not?
Well, let's go simple to more complex, maybe.
Yeah, they would be. They would be, but let's see. Yeah, so if we have two processes, A and B, which you know, one process is the 0 process, and another process is 0 in parallel with 0. Those are effectively structurally equivalent, right? So A should equal B, which is true in my implementation. Now, if we quote those processes and create the name that is the quote of A and the quote of B, those should all, gotta put some news in there.
It's not a case class?
Not anymore, not in my implementation, no. Yeah, then so that is also true. Those are name equivalent because the underlying processes are structurally equivalent.
Any particular reason you didn't use a case class?
Yeah, we can. I mean, we can get into that.
Okay.
I think let's maybe get into that a little bit later.
Okay. Anyway, so Glenn, that's an example of name equivalence, right?
Okay, yeah.
So right now we're saying that a process can reduce if there is an input and an output, and they are both listening or intending to receive on names that are name equivalent. They can be, you know, different processes in that the grammar that constructs them is different, but what we're looking at is that they're name equivalent, and that's a calculation in sort of our it's a calculation which uses structural equivalence, and that's how we decide if we can reduce them onto across two names. So the point is that we don't have to use the relationship of name equivalence to say that that's how the two things meet and reduce. We can define any other number of relationships that describe pairs of channels. So any set that gives us pairs of names, we can use that to say that reductions happen when the input and outputs are like members of that set, or that tuple is a member of the set. So one relationship, let me share that again. Okay, so are we understanding then this first COM rule? Or Glenn, does this make sense now that the names have to be name equivalent, or they have to be just the same name for a reduction to happen?
Yeah.
Okay, so that's our precondition.
Yeah.
On
Okay.
names.
Yeah. Of course. Yes. Okay.
Yeah,
Sorry.
great.
Yeah.
So now we're changing that precondition. So we're describing these names in a different way by saying that right. We're saying that our names are quoted channels P and Q down here. So we're saying that the quoted process themselves, if we put the output channel and the input channel next to each other in a par context, and they eventually reduce to 0. That's what this whole thing says, which we can get into how it says that in a little bit. But if they eventually reduce to 0, then we'll say that a communication can happen across those two channels.
On the top line, how would they reduce at all if we didn't have? So there must be some other way that they reduce, because now we're defining the COM rule, right?
Yeah, so they are reducing using the same COM rule, and so you have to define at some level that bottom level process, which is down here, which is what Greg describes. But yeah, it is this rule alone, without anything else, yeah, is a mutually recursive equation that doesn't have a ground. We'll describe the ground in a little bit. But what it's actually saying, sort of in terms here, it's saying for all processes R, such that process P and Q in parallel with each other reduce in 0 or more steps to R.
Well, that's what I'm trying to figure out. How would they reduce at all if there's no COM rule? Because it's saying consider an alternative calculus without the COM rule above, right?
Yeah, it's this same COM rule right here.
No, it says consider, for example, a calculus identical to the one presented above, but with an alternative rule governing communication. So it doesn't have the above COM rule, right?
This is a precondition. So this is saying, given something of this form, we can reduce here. It is this COM rule. It's our new COM rule.
I see what you're saying. So if it reduces using the new COM rule, then it reduces using the new COM rule.
Yes.
Okay.
With some extra stuff in between there, but yeah, it's saying that if we have two names which their underlying processes annihilate to reduce to the 0 process by 0 or more steps, then we can reduce across those names.
And how can we define this this new COM rule on the top? This R. What is this R?
It's any process.
Yeah, R is any process. R is any reduction of P par Q.
So this COM rule is not the same as the first one, like rather equivalence of names.
Exactly. Yep. Exactly. It's different. So this arrow here is the same as this arrow below hand. So yeah, it's a recursive. This is a recursive equation right here. So yeah, I guess we could.
Okay, and the way that the first arrow on the top could happen is by structural equivalence, not by a COM. That's the way it gets off the ground, I guess.
Yeah, because you say, right, so that's where it's talking about down here, that if you have 0 par 0, that reduces in 0 or more steps. In fact, it reduces in exactly 0 steps to 0. And there are no other reductions. There are no reductions to the 0 process. So that means so if up here in this equation, our P channel, it's probably good to write this out somehow. I don't know how I can flip back and forth between these easily. Maybe just try to share my whole desktop, and we'll probably get gross tearing, but that's okay. For now. So, right, I'm just gonna type for all R, and we're going to give a specific example here. We're going to set P is equal to the 0 process and Q is equal to the 0 process. And we're going to check to see if, so for all R such that, so for all R 0 in parallel with 0 reduces 0 more steps to R, that has to imply that R reduces at some point or has a potential reduction to 0. So we can say, we can check to see so yeah, we can check to see that can the process at 0 bang Q parv for Y from at 0 P. So we can ask, does this reduce with our new COM rule? And so to do that, we have to check this top precondition to see if it applies. So we're saying, does this is this making sense so far?
Well, so why did you write Q instead of 0 and P instead of 0?
Because we don't care what they are.
Yeah, we do. On line 1, you just said what P and Q are.
Oh, right. Okay. Yeah, that's true. But they're different. Sorry, because this is P channel and this is Q channel. And this is P and Q. They don't necessarily have to be related to each other.
Okay, I think
you want a Q there.
Yeah, Q.
Yeah, thank you. Okay, so yeah, our
so P channel and P are not related in any necessary way. They're just different things.
Yeah, yep. That's my understanding. Is that this Q channel and Q aren't related in just that Q is the output process, is the output guarded process, and P is the input guarded process, and Q channel and P channel are the names at which those output and input guarded processes live.
Well, I told you.
Anyone else? I want to make sure that we explain this before, or that we understand this before going forward. What I've written down here. We're checking a specific instance. So now, yeah?
Right, so now we got to find all the things that 0 par 0 reduces to, right?
Yep. So we know that 0 par 0 actually doesn't have any reductions because it's just the 0 process, and the 0 process doesn't have any reductions.
Well, for example, it reduces to 0 par 0.
That's not a reduction.
It's equivalent to.
Yeah, a structural equivalent is not a using the rules of structural equivalence to get to a different syntactic form of a process is not a reduction.
Yeah, they're equivalent.
Really?
Yeah. Mm-hmm.
You can think of it as it's not a reduction.
So what can we use for reduction? Just the COM rule?
Where's that? How would I know that?
Because it's not a computational step. They're two different things. There are structural equivalences and there are reductions. Structural equivalences are sort of two-way relational rules. So reductions, you can think of them as if from the output you cannot regenerate your input, then it's a reduction rule. It's a computational step.
Where would I learn that though?
I don't know. I guess maybe
I'll have to go find that somewhere.
Yeah,
it came up in Greg's lectures at least. I don't know that it's in this paper.
Yeah. So 0 has no, it reduces in 0 more steps. So R, the only thing that R can be is 0, right? Because the process 0 par 0 reduces in 0 more steps to only the process 0. And it's exactly 0 reduction steps that it takes to get to that process. So
that confuses me too. How does it reduce in 0 steps?
Because it's, what do you mean, how does it reduce in 0 steps? It is 0 par 0 is structurally equivalent to 0. So it doesn't require any reductions to be 0. And so that's what this means here. This this arrow, left or right arrow star, means 0 or more reduction steps.
Yeah, I guess I got to find out what a reduction step is. How can something that's not syntactically the same thing reduce in 0 steps? That doesn't make any sense to me. I just don't know what that means.
So P, always, right, reduces in 0 more steps to at least P. Could be other things as well. Just because when you do not reduce at all, you just get the input that you've started with.
Okay, then R could also be 0 par 0, right?
Sure.
Okay.
It's something structurally equivalent, to 0. It could be 0 par 0 as well. But the point is that given our structural equivalences, we know that if P channel is 0 and Q channel is 0, that those all reduce in 0 steps to 0. So that's our bottom term for this recursion. So quote 0 can serve as its own co-channel in this model. And so we can find more pairs from that, because we have a bottom set here. We have a reduction that can take place. So our answer is that does reduce, yes. And it reduces to P with quote Q substituted for Y. Is this becoming more clear, or have we muddied the waters? I guess Glenn and Joshy.
I think it does.
Yeah, it's helping me a lot. That's great. I'm curious if you can help me with the vocab. What would I say, like something annihilates something else? Would that be P and Q?
Yeah, P channel and Q channel, they annihilate each other. Just, I guess annihilate means that they reduce in some number of steps to, or they are able to reduce in some number of steps to the stopped process.
I'm not completely clear how they are reduced to 0 always. I mean, if they are like communicating, why they need to reduce to 0?
It's saying if they reduce to 0.
Oh, okay.
Then this communication can happen.
So one thing that it doesn't say, which this tripped me up for a while, it does not say that the process that results from your communication is going to reduce to 0. So this P with that Q substituted for Y It says nothing about that annihilating itself and reducing to 0.
Oh, it says that.
It just says that the names
Yeah,
that were communicated across,
which are processes.
which are quoted processes. When you put those quoted processes in parallel, those can reduce to 0. That determines when a communication can happen. But yeah, it does not say that. It does not guarantee that this process here will reduce to 0.
I have in case it's hard to read just the sort of if-thens and stuff, the top line is an if-then itself. And you can think of it as like, if every time it rains, I pick you up in my car, then I'm a good guy. That's all the top line. And then the rule as a whole says, if I'm a good guy, you should let me into the bank.
Yeah, this helps. Yeah.
Yeah, because this is an implication here, right? So it's, if this, then that, and then if all, and then the whole bar line says if all of this, then this.
Yeah, it makes sense.
Yeah. All right. Yeah. Now,
Thanks for diving into that. That was very helpful. Thank you.
So to dive, I guess, one step even a little bit further, is that there's nothing special about like reducing down to the ground level, right? We could just define some set of processes, which are determined that are in the set S of A, and then say that if we annihilate down to our set, if we can reduce to some sort of process which is in that set, that determines how that we can communicate across these channels. So I think the really cool thing is that we can, since we have this amount of structure that we have on the names that we're communicating across, we can talk about our COM rule by using the behavior of the sites at which the communication happens to build our communication rule. And we can use the same language for both.
So I get that this is a cool thing to do. Are these new COM rules different from the original COM rule in any way?
Well, they're different in how they're defined. They're not different in the effect they have.
Yeah, okay. That answers my question.
Is this what Greg was getting at, where the example of HTTP over TCP and TCP versus HTTP?
Yeah, so it gets closer to that. Yeah, I think he's building off of that notion when he's talking about here, I'll pull up another image here. When he's talking about this stuff, about having these process contexts, right? So yeah, I haven't pieced both of those things together fully yet, but I think I'm getting closer. But if anyone else is further along and wants to say more about that, please do. But this here was where Greg was talking about the TCP over HTTP, that kind of thing, saying that we have this definition of a context, which is just a process with a hole knocked into it. So it's a process that we can add another process to, that returns us a process, and that we can define communication rules where instead of messing with the stuff on the left like we were before, we start now messing with the stuff on the right by saying that we supply a context. So we supply essentially a transformation of a program, and we apply that transformation of the program when we do our substitution. So say that, and I think where he's getting at, and why I was saying I think this does apply, is that we can compose these two ideas of like having a COM rule that messes with stuff on the left that talks about the names that are being communicated across, and we can have something that messes with the stuff on the right, which talks about what substitutions are actually taking place, and sort of use both of those notions together to make a whole bunch of interesting types of COM rules that can be composable and that can represent these hierarchies of systems like biological systems and that sort of stuff. So yeah, I guess does this COM rule, where you're wrapping up any process that's sent into another process that you've defined, does that make sense? Or what questions do you have there?
Yeah. This context stuff only makes a vague amount of sense. I think it made sense when he was explaining it to some extent, but.
Yeah. So a context is, I think what this is saying is that com sub k is like a given context that we create, and a context is just a program. It's just a rolling process with a hole in it that we drop a rolling process into. So say that.
Well, a context is either double square brackets or 4x or 4x for y from x in a context, or you can, I forget whether bang is send or receive all the time. That's send. Send. You can send a context, and you can have a context in parallel with something. I don't understand why the context only goes on one side, but.
I think that's just a notational, because they would be structurally equivalent if they went otherwise. So it just, yeah, it takes the structure of row calculus, but puts holes where processes can be, if I have that right.
Yeah, and I think that this was just because he was going quick. I'm pretty sure that, am I sharing my whole screen here? Can you see the terminal?
Yeah.
Okay.
Oh, the terminal, no. Not the terminal, just the Greg's slide.
Oh, okay, yeah. So I think, I'm pretty sure what was meant is k comma q : equals, and then the rest of that stuff.
What is p slash square brackets?
So that is when we take our context and we apply some process to that context, then we are given back a context with p substituted for all the place where the square brackets were. So say we had a context equal to,
okay, substitution. Okay.
I don't know I don't know that he meant k comma q, but
yeah, maybe.
But I think he just introduces this k so that you can introduce the whole.
Yeah, I took q as still being a normal process in the context.
Okay.
Yeah.
That could very well be. So Q is just sort of our traditional process construction rules.
I think so.
Well, it's independent. I mean, that definition of K doesn't say what Q is.
Right, right. But I was wondering if he meant to wrap up Q into that same definition, or if that he meant for that to still contain. Yeah, I guess. Yeah, it should be parametric in the notion of process, but I suppose it should be parametric in the notion of process. Yeah. So, but.
Okay.
So say we
because he's defining what a context is. So that if you imagine it like a stopped execution, like where are we? You know, the debugger type of thing. And so the K is kind of defining the state of the debugger when you stop.
Right.
That's my intuitive sense of this.
Yeah.
And pointing at a given spot in it.
Mm-hmm. That makes sense. Yeah, the way I think about it is that, like, in the TCP HTTP example, or that, like, we need a communication adapter example, let's say that, like, P has, so for Y from X, P, that's our input process here, and say that we're expecting Y to be, I'm just trying to think of what a good example would be. Say we want to drop Y and say that we're expecting whatever we receive on Y here to expect Y to be of the form, or expect drop Y to be of the form P par, and then maybe like X. So say this is just like what we expect our process to do, but we want to be able to accept as sends processes Q that do not that are just of the form P, that and there are no sends on X. So we could define a context which is equal to we have a whole, and then we have an X bang whole. Right, and we'll call that context just K1. So now we can say that we can use our COM rule to enforce this behavior of expecting drop Y to be of this form. By saying that whenever a reduction happens, we are going to take, so here's our context, here's our thing that we will reduce. It will be for Y from X, drop Y in parallel with X bang Q. And then when that reduces via our new K1 reduction rule, we get our process P, which is drop, and then Y is the thing that we've substituted. So let's say P equals drop Y, right? And we just take P, and substitute context Q for Y. So now drop Y becomes at context Q is what we're dropping, which becomes Q or bang. Right. Does that help?
Oh yeah, this helps.
Cool. So yeah, we're allowing like insertion of code into our communication rule. We're allowing our communication rule to formulate the thing that's being output, the coded process that's being passed around, and manipulate it before substituting it into the input guarded process.
That was tremendously helpful for me. Thank you for doing that.
Cool. I guess, do we want to spend the last like 8 minutes here talking about the Scala implementation that I have, or would we like to do something different?
I've been staring at it.
Okay, cool.
The class for process, was that inspired by the gRPC definition?
No, I mean maybe, but like subliminally. But no, I wasn't thinking about that when I did it.
So you just sort of made it up?
Yeah. Yep. I was trying to create a class which only contained information via the equals that that included structural equivalences, and erased all other information about terms that wasn't needed. Does that make sense?
Can you show on the examples in the Scala case?
Yeah. So I have some, I guess, well, I'll just start from the top here. I have my types of inputs, lifts, and drops. Inputs, well, let's do the outputs first, are of this type frequency map, which is something I defined, and then I realized that there's an actual term for it. It's a multi-set. So it's in a multi-set of a tuple of names and processes. So, right, if we have x bang p, par x bang p, then our lists would be represented by the tuple of x bang p mapped to the integer 2, telling us that we have 2 of those. And I'm using the notion of multi-set because we don't care about the ordering of the things in p par q, and then I'm just deciding that I have, instead of one big set or multi-set that contains all of my inputs and my drops, I'm just going to separate those out and keep those sorted into 2 different multi-sets, but that really shouldn't matter. I realized at first I only had, and then the inputs is also a multi-set that has just a singular name in processes, because when I construct an input process, the bound name of that input process, I realized that you can't really keep that around in my representation. You need to substitute it for something. You can essentially give that name an identifier that's indicative of its location inside of the process. Maybe that might be clear a little bit later, but I essentially wanted to, when you're binding a name via input, it really shouldn't matter what that name is anymore, because it's bound at a top level and it's replaceable by any other name, and you still get the same meaning, same structural equivalence of a process. So
it's kind of nifty that this works out and everything. It's not sort of self-evident that this is the row calculus.
Yeah.
Okay.
That's true. Yeah. Which, yeah, I mean, that's sort of a little bit what I struggled with, is that, you know, I ditched this. There's more of a leap that you have to take now from getting from the grammar to the this representation, because this representation doesn't actually hold the grammar that, or the syntax that constructed it. It erases anything that's not structurally equivalent.
Right, but that would be a straightforward. You could prove it by writing that program, right? You could take the obvious representation and convert it to this.
Yeah. Yes. Easily, right? Because I have all of the. So the sealed process class. This isn't actually something that you would construct when you are looking at a grammar. This is just sort of. I'm telling you what my internal representation of a process is here, and it's that we have some number of inputs, which are essentially only determined or only uniquely identified by a name that's being listened on, and a process that follows. And then we have lists, which are uniquely identified by only a name that's being output on and the process that's being sent. And then I have the number of drops, which are the unquoted names that are in that context. And then I also store a height of the process, which just, it's the height of process 0 is 0, and the height increases whenever you put an input guard in front of something. That could be calculated on the fly, but I just store it for ease of use. And then I'm saying if that my inputs, my lists and my drops are the same, then we have a structurally equivalent process. So then we get into how we actually define the grammar. We have the trait of a name here, and then we have a name is either a quoted process, and it's interesting that, yeah, we'll get into that in a little bit, but it's either a quoted process or a bound name. In a bound name, I'm just using an int to signify it, because I could theoretically keep remove this notion of bound name, which is just sort of defined by an integer, which is going to be the height later, and use a quoted process, and then sort of have a map from the real set of integers to the quoted processes, right? So there's examples that I think even has out there of how you can create, and I think actually, yeah, Greg's OCaml implementation too has like you can define a stream of processes or of names, which essentially just map each process to the integers. So like the integer 0 is just the name at 0, and then you build up from there. So yeah, my Scala style isn't great. I'm working on developing it, and I got a couple suggestions, but if you have more as we're going through this, I'd love to hear it. But so the 0 process has no inputs, lifts, or drops, and has a height of 0. The drops process, I just put the name that we want to drop into our drops. The parallel, I merge the maps, which is I essentially, it's a union of the multiset for the inputs of the processes that I'm powering and the outputs of the process that I'm powering, and the drops. And the height is the maximum height of both those processes. And then the lift operation, we just put put the name and process into that into our map of lists or multi-set of lists. And then input is where it gets a little bit interesting, because now I say that when you give me an input of the form y from x dot p, I need to do something with that bound name y, because I need to erase y itself. And the way that I do that is I substitute for y a new bound name that's determined by p dot height, so that will make that bound name unique in the process. And then that's what I store into my inputs multi-set. And substitution is defined here. I think it's pretty straightforward. And then, yeah, reductions. So one of the interesting portions was that I before hadn't really been thinking about dropping a quote as a reduction step, but I think it actually might be a reduction step. Just because once we have,
Greg just
it is
that way in Boulder.
Okay, cool. So yeah,
Tom rule and eval are the two things in the row virtual machine.
Okay, yeah. Then yeah. So I hadn't been thinking of it that way before, which made this a bit interesting. But yeah, so I can redefine my reductions such that that's a step, and that actually makes me a lot happier with my implementation of reductions. But yeah, you can't just yeah, you need to be able to bind whatever is in a drop. So, right, if I have, let me give an example. So if we have a process where we drop the name at 0, that is not structurally equivalent to a process where we, yeah, this is not structurally equivalent to just the process 0. Because if we say take this equals p. So,
oh, I see. Okay.
So if this is our p, then where was I going with this? Oh, then if we take for at 0 from x p, then I think it's easier to see that that's, you know, that's not equal to for at 0 from x 0, because what actually the semantics of this is that whatever we receive on x, yeah, drop. Great. I think that yeah, this should make it clearer that that these two things aren't equal. Because what this is saying is that we are going to run whatever process we receive on x. So we need to somehow, we're not, in my Scala implementation, when I create this drop, I can't just take all of the inputs and outputs and everything and merge them into my top set. I have to save them around somewhere so that I can allow further grammatical constructions that use that name to bind that name.
Yeah, he says that in one of the papers that something or other is not But one of them is, yeah, quoting is opaque to substitution, I think is.
Mm-hmm. Yep. So that was also the reason why in when I have a so when I have a quote, when I quote a process, if that process has any drops inside of it, I have to say, okay, actually, I have to run those drops. I have to put them all in that top level context. I have to erase that those were names that were dropped, because you can't, once it's quoted, you're still opaque to substitution. And, right, yeah, I'm actually not totally convinced of this yet. But that was the way that I implemented it. Okay, we're a bit over now, but any other thoughts or questions?
Just on a Scala thing where you say input _1 _1.
Yes.
You could have a structured pattern instead of input, you know?
Yep, totally. I just got that advice earlier today, and I'm going to take that. Yeah, so thank you. Yeah, that'll make things a lot more readable.
Can you just say about the height? The height is when the process is nested inside the other process. For example, is another height if process is inside the for?
Yeah.
Like a P?
Yeah.
This is another height, but this in R, if you have a R, this is the same height, right?
Yeah, so a process inside of a for and outside of a for, that's the only thing that determines height.
And there's only one bound name.
Or, for example,
there's only one name bound at each height?
Yeah.
Yeah, right.
Right.
I mean, in row lang, that's not the case, but in row calculus, I guess it is.
Mm-hmm.
Maybe it is in row lang too. No.
how do you mean in drawing is not?
It's polyadic, right? Is that the
Well,
term?
not only that, but there's patterns. You can bind several names at once, you know, by using a pattern.
Right, but you could still. I like to think of it as the height is the thing which you need to uniquely identify. The height and the input process is what you need to uniquely in the polyadic form. You could uniquely identify the height, and the name that you're listening on can still uniquely identify all of your bound variables at a particular height. Right, because you can't.
There's one point where you said bound name p height, and you said you're guaranteeing that that's different from all the other the names. That's only true if there's only one per height, I think.
Yes. Yeah. Well, so if you have you can have a process that is a par of two processes. They're each input guarded processes. There are sort of two sub processes with height 1, and there are two names that are substituted for that inside of that. So there are two height 1s in that process, but that doesn't matter.
Right. Yeah.
Yeah. Cool. Yeah, I'm gonna have to think more about quoting a process that contains drops inside of it, and how you do name equivalence across those, because I'm not sure that my implementation does that correctly right now.
Has Greg seen this?
I sent it to him.
Okay. You also might look at the actual RChain code to see if basically, because like I said, the structure you picked for process is very similar to what they picked in the gRPC representation. So it could be that this code is in the matcher or something roughly.
Okay, cool. I'll look at that. All right. Well, thank you, everyone. Good to have you.
Yeah, thank you.
Thank you.
See you next week.
See you. Bye-bye.